Okay, well, good morning. Today we'll take a look at just some kind of basic concepts and ideas related to modeling and machine learning. And so, what is machine learning kind of in the first place? And so I took this from Wikipedia, and it says something like this. It says machine learning is the scientific study of algorithms and statistical models that computer systems use to effectively perform a specific task without explicit instructions, relying on patterns and inference instead. I think all of this is just to say that we try to fit models to data. And yes, we ask the computer to kind of perform a task without explicit instructions in some regard, but humans are still required to kind of specify the model, specify what direction to pursue, but then we leave a lot left up to the data and the algorithm used. Okay, and so when the machine or the computer or whatever you want to call it ends up making decisions based on the algorithm, we might call that the machine learning. Okay. What is a model? Let me see if I can move that. Okay. So this is a picture of a model airplane. And so, in general, we'd just say a model is a simplified representation of something complex. Okay. And when we're talking about statistics and we have statistical models, a statistical model is a simplified representation of some kind of complex real-world process that generates data. Okay, so there's something that happens in the real world that produces numeric values. Okay, and so it could be something like I don't know, let's say the data you're looking at is how tall are people, okay? How tall are people? And so when you think about that data, some people are short, some people are tall, some people are average, things like that. What is the process that ends up determining how tall someone is? Okay, well, it's kind of complicated. Why are you the height that you are? And you can say, well, my parents are tall, okay? But that doesn't explain everything, because if you have siblings, you and your siblings aren't all exactly the same height. So parents aren't the only answer to that question. There's other factors, right? Your own nutrition, other environmental factors, and then as far as parents go and genetics, there's still a random component to it. And so, can you could you take someone's DNA, put it through some kind of machine, and have that tell you exactly how tall this person's going to be? Also, no, right? There is some kind of complicated process that went into determining how tall you are today. And as far as a statistical model goes, is we're going to just try to simplify that. Okay, we're going to just try to say, you know what? Let's forget all the tiny little details, but let's just have like a simple kind of factor. Let's take in your mother's height. Let's take in your father's height. If we know those values, and we'll just kind of average them, add a number or something like that. Okay, and we'll just create a simplified representation that says, hey, you know what? This is good enough as far as explaining why some people are the height that they are. Okay, it just includes a subset of the variables in the real life process, and that outcome, whatever number we're predicting, always includes kind of an error term to say, yeah, you know what, this is kind of what my model predicts, but we got to give it some wiggle room. Maybe it's going to be a little bit too high, maybe it'll be a little bit too low. Okay, and so we always have an error term to kind of account for everything else. And so as far as statistical models go, here's a quote. It says, "All models are wrong, but some are useful." Okay, and these models are often useful in either we can use them to make predictions, or we can also use the model to gain an understanding of the relationships that exist between variables. A lot of times we have to choose which of these objectives to prioritize, and you have different models that fit, different kind of statistical models that fit one of these objectives a little bit better, okay? So, for example, linear regression is a statistical model. Linear regression is really good at the second part, gaining understanding of the relationships between variables. You create coefficients and you create interaction terms and things like that, and you can start to gain some insight as far as not necessarily what causes the other. Okay, we don't try to draw cause and effect relationships in linear regression, but we are able to say, hey, you know what? If this variable increases by 1, our prediction goes up by, B1, right? Our slope, something like that. We have a whole bunch of other models that are designed to make accurate predictions. Things like neural networks and a lot more of these complex machine learning models are designed around how to make accurate predictions. And if you say, hey, can we use this model to understand what's going on between the variables? The answer is going to be no. It's a mystery, and nobody really understands what's happening inside the network there, okay? We have a textbook. The textbook, let me pull it up here, is our first course in machine learning. It looks like this. It's carried by the bookstore, but you don't have to buy it at the bookstore. But yes, please, you can find it in different places. We'll just leave it at that. Okay. But anyway, in that textbook, there's an example, and we're looking at data from the Olympics, and we're looking at the 100-meter, men's 100-meter, race, track and field event, right? So this is where like Usain Bolt sets world records and things like that. So we're looking at the gold medal time for the men's 100 meters track and field event. And there's all kinds of things that ultimately factor into the winning time. One of which is who's actually running and things like that. But we can kind of plot what these winning times were over the years. And so I guess as far as modern Olympics go, the first one was held in 1896 or something. And the watches, as far as recording, they didn't have very precise measurements. So it was 12 seconds. And then in 1900, the gold medal time was 11 seconds. And then they started having kind of accuracy up to the 10th of a second. And then now we have, accuracy up to like the 1,000th of a second. But here plotted over the course of time from 1896, and I think this went up to 2012 or something like that. What we see is this general trend that as time, as the years have progressed, it seems that overall the gold medal winning time has gotten faster and faster. Okay, it's not every single year that you go, it's faster. If you look between say 1930 and 1950, it kind of stayed relatively flat. Actually, it got a little bit slower over here, but then after 1958 or whatever, 19 something, 56, it started to decrease over time again. This is what we want to do, is we just want to fit a simple model, okay? And so a very simple model would be something like, overall, race times have gotten faster as the years have progressed, okay? I'm gonna start with a linear model. You guys are already familiar with linear models. Everybody took 101A, I believe. Okay, some of you have taken 100C. Okay, well, it's okay if you haven't. Some of today's stuff is going to overlap with 100C, and when you actually do take 100C in the future, if you do take it, you know, you'll get a little bit of overlap. Repeating some of the same concepts in multiple courses, I think is fine. But anyway, we're going to just say, hey, you know what? Let's make just a simple model. We know it's not that, like, as years progress, humans get faster. That's not the answer. It's not like we're going through some, I don't know, physical evolution to be running faster. But, you know, different things happen, right? Like they improve the technology of shoes and, I don't know, the material on the track and, I don't know, different things, maybe training regimens and stuff like that. And they've been able to eke out tiny bits of extra performance and things like that. And we're just going to simplify it, okay? And we're just going to say, hey, you know what? If you wanted to predict the winning race time, just tell me. Was it 1960? Was it 1990? Was it somewhere else? Okay? Let's try to predict the improvement. A linear model says that, okay, you want to take in the year, you want to make a prediction. A linear model says how much you're going to adjust your prediction remains constant throughout the entire data set. So the amount that you would adjust going from 1900 to 1904 is the same that you would adjust going from 1992 to 1996, okay? That's what it means to have a linear model, that when you, you know, whether you buy one additional, say, banana, okay, if you go, the amount of, it's going to cost you to go from 5 bananas to 6 bananas is going to be the same as it costs you to go from 5,000 bananas to 5,001 bananas, okay? You're just going to add one. Not everything in life works that way, right? If you were going to place an order for cookies or something, or maybe like t-shirts, like if you're going to get custom t-shirts printed, that first t-shirt will probably cost you like $40, okay? But if you're going to say, I'm going to place an order, and if you want 2 t-shirts, maybe the second t-shirt costs you an additional $20 or something like that, okay? But then if you're going to order 4,000 t-shirts, you know, that one extra t-shirt going from 4,000 to 4,001 t-shirts, that extra t-shirt probably will cost you an additional like $3 or something like that, okay? So, you know, in the beginning, because I don't know, setting up a custom t-shirt, you got to set up the press or whatever. So, you know, a lot of other things in life, you know, the more you buy, you know, the later ones don't cost as much and things like that. So that a linear model would not work there, okay? But a linear model here just says, yeah, you add 1 over here, going from 1 to 2 is the same as going from 100 to 101 to 102. Okay, and so I think that's what I've written. If I predict the time improves by 5/100ths of a second going from 1920 to 1924, we're also going to predict 5/100ths of a second or something like that, okay? Now, obviously, we can't predict far into the future because far into the future, we would end up getting negative race times, and that just doesn't make sense. But as far as the range where we have data, this could still be a useful model. The linear model will fit a straight line to this data, and so when you try to create the equation for a straight line, what you need are a slope and an intercept, okay? And so when we say we're going to fit a model, to our data, what we're saying is we are trying to estimate what these model parameters are. So in this case, we need a way to estimate what is the slope and what is the intercept. That's what it means to fit a model. This is figuring out what your model parameters. In our case, we got 2 parameters. And what we want to do is we want the resulting line, the resulting model, that the slope and intercept, we want it selected so that it does the best job of fitting the data. And so now we have to define, what do we mean by the word best, okay? When we say we want to fit the data, and we want the line that best fits the data, we need to define, okay, what does it mean to have the best fitting line? And so in linear regression, the definition of best is the line that minimizes the total squares of residuals, right? So this is your least squares regression line. It's the line that minimizes the sum of squared residuals, or the mean squares of residuals would just be this multiplied by a factor of n. So we're going to say our residual sum of squares is the difference between the actual value, we'll call y sub n, what our model predicts, which is y hat sub n. Okay, so for every value from n equal 1 to big N in our data, we want to calculate what's the difference between the actual and the predicted value. We take that difference, the residual, we square it, we add them all up, okay? And so this is going to be the line that minimizes the squares of residuals. Why do we do the squares of residuals and not the absolute values? Yeah.
Absolute values always add up to 0. Yeah.
The absolute values don't always add up to 0 because you're turning them to absolute values. Yeah, just the pure deviations always add up to 0 around the prediction line. Well, not necessarily around the mean, I guess. Anybody? Squares over absolute values? We didn't learn this in 101A, maybe? Okay. Well, I mean, there's several reasons, okay? The mean minimizes the, as far as measures of center, mean minimizes the value that minimizes the squared deviations from the mean. So if you say we have some measure of center and we want to minimize some kind of quantity, the mean is going to minimize the quantity squared deviations from that measure of center. The median minimizes the absolute values from that, from whatever absolute values of deviations from the center. If you want to solve via calculus, the squared, you can kind of take the derivative of the squared residual function and set it equal to 0 and solve. Whereas if you have the absolute values, you get this kind of discontinuity in the, because you get that corner. You know, trying to solve it via calculus it gets a little bit tricky. Also, if you use the median, depending on the thing, you will not necessarily have a unique solution, okay? So, you know, oftentimes when we say, you know, find the median of this set of numbers, let's say 1, 2, 3, 4, 5, 6, okay? And you have 1, 2, 3, 4, 5, 6, and we say find the median. The median is any value that splits the data into 50, half the values are below and half the values are above. We often say use 3.5 because it's conveniently halfway between 3 and 4. But technically, any value from 3.001 to 3.999 could count as the median of your data set, okay? Just using the definition that the median needs to be a value that splits your data into 2 portions, one that's above and one that's below. And so the median doesn't have a unique solution. We conventionally define the median as being halfway between your 2 most points, but using something like, we just need to do this, if you any value between 3 and 4 would balance out the absolute values of deviations. And similarly, if you try to fit a trend line using not squared deviations, try to fit a trend line using absolute values of deviations, you will not necessarily have a unique solution either. Squared residuals, you will end up with a unique solution. But anyway, this is how we've defined our loss function. There's a few other things. A consequence of using squared residuals is that outliers have a major impact on the resulting trend line. Okay, outliers do have a major impact on the resulting trend line. You know, the median is robust to outliers, right? Like if you have 1, 2, 3, 4, 5, 6, and you change that 6 to 6,000, the median would still be 3.5 or some number between 3 and 4, right? But as far as the mean goes, 1, 2, 3, 4, 5, 6, your mean is 3.5. But if you change that last number to 6,000, now your mean is, I don't know, 6,000 divided by, close to 1,000, okay? So the mean is dramatically affected by outliers. And similarly, when you fit the linear model, it's dramatically affected by outliers when you use squared residuals, versus if you were to use median absolute deviations or just absolute deviations, it would not be as affected by outliers. Different kinds of things. But anyway, this is what we're doing. We want to, we define our best fitting line using residual sum of squares, okay? Sum of squares of the residuals. And we're going to say we want the y hat selected in such a way that this quantity, our loss function, is minimized, okay? And so this example of linear regression, we can think of it as an optimization problem. There's a thing and we're trying to minimize it. The total sum of squared residuals, we're trying to minimize that, okay? And a lot of things in general, a lot of machine learning algorithms can be framed as optimization problems. We have some kind of objective function, and we are trying to minimize, or in some cases maximize, that objective function. So I think the title of this class is Computation and Optimization for Statistics or something like that. But yeah, a lot of kind of machine learning can be boiled down to optimizing something, optimizing your cost function. All right, let me give you your first view quiz answer, which is the letter B. B as in bear. B is your first view quiz answer, B. When you look at the textbook, it chooses a certain notation for the model, and so I'm going to try to match the textbook's notation so that when you go review the textbook, so as you study for this class, read over my lecture notes. Also read the textbook, okay? Also read the textbook. And so I want to kind of make sure my lecture notes match the textbook and don't confuse you. So as far as the textbook goes, we're going to say the values predicted by the model are going to be written like this, okay? So here I wrote, y minus y hat. But here we're going to say, okay, the values predicted by the model are going to be the result of some function, f, okay, where we plug in the value xn, x sub n, and there are two parameters that we need. We need a slope and an intercept. The slope is W1 and the intercept is W0. These, you're accustomed to using, say, like beta 0 and beta 1. This is more generic in that W is just a weight, okay? Weight 0 and weight 1. It's the same thing as intercept and slope, but it can be generalized to any other kind of model where you just have these different numbers, and we just call all of these different numbers different weights, okay? So basically, this is just the equation of a line, and so we're going to say the predicted value y hat is going to be the result of f applied to xn using parameters w0 and w1. The actual value y, according to our textbook, their notation, they use the letter t as in target value, okay? Because this is the value that we're trying to predict accurately. This is our target. So we have target minus predicted value, quantity squared, summed up. Rather than doing this total sum of squares errors, we multiply by 1 over n. So this becomes the mean squared error. It's going to be the same results, the same values that minimize. The total sum of squares is going to be the same thing, same slope and intercept that minimize the mean squared error. It's just over here we just have a factor, 1 over n here. All right, is that okay as far as the notational change? All right, so that's what we've got. Another very common measure that people use in machine learning models is RMSE, which is just the square root of the mean squared error, root mean squared error. And because the square root function is monotonic, any value that minimizes the mean squared error will be the same values that minimize the root of mean squared error and vice versa. So, so you have that, okay? It's just people sometimes prefer root mean squared error in the same way that people prefer standard deviation over variation, because if you have units, root mean squared error and standard deviation are measured in the same units versus variance is measured in the squares of the units. So if you've got something like dollars, okay, variance is measured in square dollars, which is kind of a weird concept. But standard deviation is just measured in dollars. You can say, you know, we got a standard deviation of $50 rather than a variance of 2,500 square dollars, which I think people find confusing. Okay, linear model. So we have the two parameters, W0, the intercept, and W1, the slope. The value predicted by the model is this. And so if I plug this in, W0 plus W1 xn, into our model, we get this. We get our loss function, the mean squared error, as 1 over n of the sum, the target value, actual value, minus what we're predicting, quantity squared. Okay? And what we want to do is we want to figure out what are the values of the intercept and slope that will minimize this loss function. Okay? So here we are trying to find what arguments, what values for W0 and W1 minimize the mean squared error. We can do this via calculus, all right? And so via calculus, we would kind of expand this. Do you guys do this in 101A? This operation? No. Okay. Maybe in 100C. Anybody taken 100C? Am I just okay? A few of you, and you did this in 100C though, right? Maybe? No? Okay. Well, all right. You did something like this in at least 32A, right? Where you have this multivariate thing and you have to find the minimum, so you take partial derivatives. Okay, so anyway, you have this function here and we say, all right, we want to minimize this. So we're going to take the partial derivative with respect to W0, partial derivative with respect to W1. You set those equal to 0 and you solve, okay? I'm going to skip all of that and we're just going to say, all right, we did it correctly. These are the answers, okay? So if you do set the partial derivative, if you calculate the partial derivative with respect to W1, you get this. Partial derivative of this with respect to W0, you get this. You set these equal to 0. You have two equations, two unknowns. You solve for these things, and basically you'll end up with some formula for the intercept and some formula for the slope, and you'll just have to take me at my word, okay? There are more details as far as doing all of the work in the textbook, and if you look up solving linear regression with calculus, partial derivatives, or whatever, I'm sure you'll find a bunch of YouTube videos. Because, you know, when you do linear regression, you have a data set with like n observations, right? You could have n being like 50 to 5,000 or a million, whatever. Calculating your sum of squares and stuff involves a summation, okay? And the summation, these things are often like annoying to have to deal with when you're doing stuff like calculus and stuff, okay? And so one thing that helps us out is rather than using calculus and using summations, we can use linear algebra, okay? Because in linear algebra, when you do a multiplication operation, that's going to be multiplication and summation combined, right? Because you go across the rows and down the column, and you kind of multiply those things and you sum them up when you do matrix multiplication. And so a lot of these summation signs, if you use linear algebra instead, will eliminate having the summation, because the summation, I shouldn't say eliminate it, okay? It just gets put into the notation of the linear algebra. You all took linear algebra at some point, Math 33A, that's like a requirement prereq for the major in the course and things like that. But it might have been a while. Maybe you struggled. Some of you took Math 115A. You got the exciting version of of linear algebra. But anyway, I always recommend this playlist from 3 Blue 1 Brown, and it covers the essence of linear algebra. And these are like the best videos on linear algebra. So if anybody hasn't watched these, highly, highly, highly recommend. I have them linked in the in Brew and Learn as well. Okay, covering things like vectors and stuff, and you know what exactly does the determinant represent, and all of these different things, eigenvectors and eigenvalues. It's pretty great. I gotta put that back into full screen. Okay. So what we're going to do is we're going to go ahead and do ordinary least squares regression with matrix multiplication. Again, if you've taken Stats 100C, this is all going to overlap with that. But if you haven't, here, I'm going to present it here, and we'll just kind of go through it. And then when you take 100C later, you'll say, oh yeah, I remember seeing some of this stuff. Okay. We are going to combine our parameters, our intercept and our slope, into a single vector W, and we're going to take each observation, which is normally just an x value. So in the context of our 100-meter foot race for the Olympics, x is like the year 1900 or something like that. Okay, and so what we're going to combine that with just the scalar value 1. And so when we say, hey, what is the value predicted by our model, okay, which is the intercept plus the slope times x1, we could say, hey, this is just W transpose multiplied by x sub n, right? Can we see that? So if I do W, this vector W times xn, this is going to return basically this quantity here, okay? And we can then do the entire x data set, okay? So, you know, you've got like 100 rows in your data or something, maybe not 100 rows, 28 rows or something. And so we're going to say, okay, our entire matrix X is all of those X values just down one column, a column of ones, okay? Here's my target values T. And then the entire loss function can be expressed like this, T minus XW transpose T minus XW. I'm going to expand that right here. So if we say, what is X times W? Here's our matrix X. We can see if I take this matrix X, which is n rows by 2 columns, okay, n by 2, and I multiply it by this vector W, which is, I guess, 2 rows, 1 column, then the result will be n rows in 1 column, where everything is going to be W0 plus W1 times X, right? So the first row becomes W0 plus W1 X1. Second row, where I've got X2, becomes W0 plus W1 X2. And these just become all of the predictions when you plug in the different X values. Okay, is that all right? If I just do X times W here. When you do linear algebra and you multiply matrices together, it is really, really, really important, okay, that you write the dimensions underneath each matrix. Because with like regular old algebra, when you're dealing with scalars, you could just switch letters around. A times B is the same thing as B times A. It's not a big deal, okay? But in linear algebra, X times W is not the same thing as W times X. In fact, you cannot do W times X. The dimensions of these things don't line up, and you cannot do matrix multiplication of W times X. You have to do X times W. And so to kind of make sure that you get it correct, always write the dimensions of the matrix or vectors underneath, and then make sure that, you know, the number of rows or the number of columns over here matches the number of rows over here, and you can get that, okay? Let me give you your second view quiz answer, A. A as an apple, second view quiz answer, A. Okay, so here I just do a few operations in R. I'm going to take the column of years, you know, 1900, 1904, whatever. I've got 28 years. We're going to bind a column of ones to them. I'm going to create a matrix W. Just initially, I'm going to start off with slope and intercept 1 and 1 or something. And I can just have 28 by 2 and the 2 by 1. And I can multiply x times W. This is matrix multiplication, x times W. The result will be 28 by 1. If I try to do W times X, I get this error, non-conformable arguments. This is a very common mistake or common error that you will encounter in R. Whenever you encounter an error in R, don't just throw up your hands and go, oh, my code doesn't work, okay? It's true, your code doesn't work, but there is a lot of information that you can get out of the error message. If you read the error message carefully, it will often tell you what went wrong, okay? And in this case, it says non-conformable arguments. And so anytime you see that error message, non-conformable arguments, it means the dimensions of W and X do not align, okay? So, and that's because W is 2 by 1 and X is 28 by 2. You can't do that multiplication. Okay, so anyway, we've got XW. I can take our target values, the actual values, our Y's or our T's, and I can just do T minus XW. T is n by 1, XW is n by 1, and I can subtract those, and the result is going to be n by 1. And therefore, if I take the transpose of this, okay, the transpose of T minus XW is going to be a row vector, basically, 1 row, n columns, and I can multiply it by T minus XW, which is n by 1, okay? And if I do that, you can see that each value is going to be basically the result of this summation. T sub n minus W0 plus W1 xn quantity squared, right? And all summed up across all n items. And so the summation of all of these things can be expressed as T minus XW transpose times T minus XW. And then if I want the mean squared error, I just multiply that whole thing by this scalar 1 over n. And so this will give me the mean squared error. So I can express my loss function as a matrix operation here. Okay. I can then expand this out using linear algebra, and I can do T minus XW transpose times T minus XW. You distribute the transpose, you get T transpose minus XW transpose. When you distribute a transpose over a product of matrices, you transpose the components and reverse the order. So XW quantity transpose becomes W transpose X transpose. And so now I have T transpose minus W transpose X transpose quantity times T minus XW. I'm going to multiply this out. We follow kind of our first, outer, inner, last, distributive property when you multiply these things. So you get T transpose T, T transpose XW minus W transpose X transpose T plus W transpose X transpose XW. All of the, I've written all of the dimensions underneath each of these things, and you can see indeed all of these dimensions line up so that everything becomes a 1 by 1, which is exactly what we want. So this is T transpose T is 1 by 1, T transpose XW is 1 by 1, W transpose X transpose T is 1 by 1, W transpose X transpose XW is also 1 by 1. We can combine these two things, T transpose XW and W transpose X transpose T. These things are transposes of each other. Can we see that? T transpose XW, if I transpose that, gives me W transpose X transpose T. We reverse them, we transpose each of those elements. And because they are 1 by 1 scalars, and if they're transposes of each other, they're the exact same value. So I can just combine them together. I arbitrarily chose the W transpose X transpose T, but I could have put in 2 times T transpose XW rather than 2 times W transpose X transpose T. It doesn't matter. But this is going to be the loss function after we kind of multiply out all of these elements. So I have T transpose T minus 2W transpose X transpose T plus W transpose X transpose XW. This is our loss function. If I multiply this over the scalar value 1 over n, that's our loss thing. Okay, are you still with me so far? Okay. So what we want to do now is we want to minimize our loss function with respect to the vector W, and we're going to use vector calculus, okay? And so vectors vector calculus, instead of derivatives, you have gradients. So I think you guys do this in 32A, right? And so you have gradients. So anyway, the derivative is basically, the limit as this thing as h goes to 0, the difference here, and then the gradient is pretty much similar concept, but now you're doing the norm of some vector h, okay? You have some function that takes in a multi-dimensional input, outputs a single scalar value, okay? And that's what we have here. So as far as the gradient goes, if you have some arbitrary vector w and you say, what is the gradient of some function? This is some scalar valued function f. What is the gradient with respect to w? It ends up just being a vector of the partial derivatives. F, what is the partial of f with respect to w1? What is the partial of f with respect to w2? So on and so forth. The symbol we use for the gradient is this upside down triangle we call nabla, okay? If it's a right side up triangle, it's delta. When it's upside down, it's nabla. So this is nabla f. This is the gradient. And so we can do this, okay? The gradient, represents the slope of the tangent of the graph to the function. The gradient points in the direction of greatest rate of increase of the function, and the magnitude of the gradient is the slope of the graph in that direction. These are some useful gradient relationships. If you have some value, a scalar value such as w transpose x, all right, assuming w is a 2 by 1 and x is 2 by 1. So if you have w transpose x, this produces a scalar value. If you say, hey, what is the gradient of this with respect to w, that's going to be x. The gradient of, say, x transpose w will also, with respect to w, is x. The gradient of w transpose w with respect to w is going to be 2w. I've got a couple of these worked out. So if w is, say, w1, w2, and x is x1, x2, w transpose x is this quantity, w1, x1 plus w2, x2. The gradient of this is going to be the partial derivative of this with respect to w1 and the partial derivative of this with respect to w2. The partial derivative of this quantity with respect to w1 will just be x1. This thing zeroes out over here, okay? The partial derivative of this quantity with respect to w2 is just going to be x2. This thing over here zeroes out. And so the result of this just becomes x1 and x2, which is equal to just x, okay? So if you say, what is the gradient of w transpose x with respect to w, you just get x, okay? Another one, if you do, say, w transpose w, you get w1 squared and w2 squared. You take, what is the gradient or partial derivative of w1 squared plus w2 squared with respect to w1? You get 2w1. What's the partial derivative of this thing with respect to w2? You get 2w2, and that's just equal to 2w, okay? 2w. All right, and you can derive the other ones yourself. You don't have to. But anyway, we left off here, and we said our loss function is t transpose 1 over n t transpose t minus 2 over n w transpose x transpose t plus 1 over n w transpose x w. And we want to say, hey, what is the gradient of this with respect to w? Okay, I've got no w terms. I got t transpose t. This is going to be a vector of zeros minus the gradient of this is going to just be x transpose t. And the gradient of w transpose x w, okay, basically is this thing, w transpose cw becomes 2cw. So I get 2 x transpose xw. And so I can combine these, and I get negative 2 over n x transpose t plus 2 over n x transpose xw. This is our gradient. We're going to set our gradient equal to 0, and we're going to solve for w. So I set this equal to 0. I want to solve for w. I'm going to add x transpose t to both sides. First, I'm going to multiply everything by n over 2. And then I'm going to add x transpose t to both sides. So I get x transpose t is equal to x transpose xw. We want to get rid of x transpose x here to isolate w by itself. Okay, this is important. There's no such thing as matrix division, okay? You cannot take a thing and divide by a matrix, okay? You can, the closest thing you can do is multiply a matrix by its inverse. That only works if you got a square matrix though, okay? So I'm going to multiply the right-hand side by x transpose x inverse, okay? And x transpose x inverse times x transpose x will reduce down to the identity, and so I will just end up getting the W vector on the right-hand side, okay? So I have to multiply the left-hand side by x transpose x inverse, and so our solution becomes x transpose x inverse x transpose t. And this is going to be the solution for W that minimizes our OLS loss, okay? And if you've taken 100C, this quantity should be familiar to you, okay? X transpose X times inverse times X transpose T. Again, I don't expect anybody to have taken 100C, but when you do take 100C in the future, this will be a quantity that shows up as well, okay? So anyway, this is the solution for what are the values of W that would minimize the sum of squared residuals. So all to say, the estimate of W that minimizes the loss function in ordinary least squares regression is this, x transpose x inverse times x transpose t. We went through the problem of solving it with kind of vector calculus, going through all of this stuff. Basically, it arrives at the same results that we would have gotten if we used partial derivatives, okay? You know, calculating the partial derivative with respect to W1 and the partial derivative with respect to W0, we would get that to there. Okay, let me, I'm going to give the view quiz answer for those of you in person, but I'm going to withhold from the video. So sorry, video people, answer the questions that you can, and please come to class next time.